Hello, discrete math fans. So now we proved that the relation induced by a partition is an equivalence relation. We're going to go the other way now. We're going to prove that the distinct equivalence classes of an equivalence relation partition the underlying set. Once we're done with this, that means that we'll have shown that the ideas of partitions and equivalence classes, they're really the same thing. They're just using different language. Now we're going to break up the proof by proving two lemmas. And the first lemma looks like this. Let's let A be a set. Let's let R be an equivalence relation on A. And let's let A and B be elements of big A. And if A is related to B, then the class of A is equal to the class of B. This is a very useful lemma just to keep in mind in terms of how you can tell when two classes are the same. All right, so here's the proof. We're going to start by supposing that A is related to B. Now, keep in mind that class of A and class of B are sets, so in order to prove they're equal, we have to prove a subset relation going in both directions. All right, so first we'll show that the class of A is a subset of the class of B. Let's let X be an element of the class of A. That means X is related to A. Now, we already know that A is related to B, and since R is transitive, we can go from X related to A and A related to B to conclude that X is related to B. And that tells us that X is an element of B. All right, so that proves that the class of A is a subset of the class of B. Let's go the other way now. Let's let X be an element of the class of B. That tells us that X is related to B. Now, I already know that A is related to B, and since R is symmetric, we'll flip that around. So we can take A related to B and flip it around to B related to A. Now we'll use transitivity. We know that X is related to B and B is related to A, and so that tells us that X is related to A, and that means that X is an element of the class of A. And so that proves that the class of B is a subset of the class of A. So we proved subset going in both directions. That proves our lemma. So we say, therefore, the class of A is equal to the class of B. That's our first lemma. And we got another lemma that we're going to state and prove. All right, so our second lemma says that if we have an equivalence relation on A, and little a and little b are elements of big A, then either the class of A and the class of B are disjoint or they're equal. So if they overlap, they completely overlap and they're the same. All right, now, in order to prove this, I think we should note that the statement in lemma 2 is really of the form P implies Q or R. Now we're going to leave it for you to prove that those statement forms are equivalent. We're going to go ahead, and what we'll do is we'll prove the equivalent statement. If R is an equivalence relation on A, little a and b is in big A, and class of A intersect class of B is non-empty, then class of A equals class of B. So that's what we're going to prove. All right, so here comes the proof. We're going to suppose that R is an equivalence relation on big A. We'll have little a and little b be elements of big A, and we'll suppose that class of A intersect class of B is not empty. Our goal here is going to be to prove that class of A equals class of B. Now, since the class of A intersect class of B is not empty, then there exists an X in class of A intersect class of B. That means X is in the class of A and X is in the class of B, so that tells us that X is related to A and X is related to B. All right, since R is symmetric, we can take this guy and flip him around to get A is related to X. And now we know that A is related to X and X is related to B, and now by transitivity, we get that A is related to B. But now, A and B satisfy the hypotheses of our first lemma, and that tells us that the class of A is equal to the class of B. All right, so that's it. So that proves our second lemma. We're now ready to move on to the main theorem. So the main theorem talks about the partition induced by an equivalence relation, and it says that if A is a set and R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of A. All right, there are two things that we have to show. So we're breaking this theorem up into two parts. So step one, we have to show that A is the union of the equivalence classes of R. Step two, we have to show that the intersection of any two equivalence classes is empty. All right, so let's let A be a set and R be an equivalence relation on A. And for notational purposes, as we've discussed before, we're going to assume that R has only a finite number of equivalence classes. The proof really isn't all that different if there are infinitely many equivalence classes, so we'll just simplify our proof here. So we'll denote these equivalence classes as A1, A2, up to AN. N is a natural number. Now let's prove step one, and that says that A has to be the union of A1, A2, all the way down to AN. Well, it's a set equality proof, so we have to prove a subset relationship in both directions. All right, let's start by picking an element in A. And according to reflexivity, X is related to X, so that means X is an element of the class of X. Now X is in some equivalence class, so it has to be in one of the equivalence classes that we named earlier, A1 through AN. So that means X is an element of A sub j for some j, and that means X has to belong in that union somewhere. All right, so that proves the subset relationship in one direction. Now let's go the other way. Now let's let X be in that union. That means X has to belong in A sub j for some j. But A sub j is an equivalence class of R, and equivalence classes are, by definition, subsets of A. So there's really nothing to prove here. We know that A sub j is a subset of A, and that makes X an element of A. So now we've proved the subset relationship in the other direction, so those two sets are equal. So that finishes up step one. Okay, step two, we need that the distinct equivalence classes of R are mutually disjoint. All right, so let's suppose that A sub I and A sub j are any two distinct equivalence classes of R. We want to show now that A sub I and A sub j are disjoint. All right, since they're distinct equivalence classes, that means they're not equal. And since they're equivalence classes of R, there must exist elements A and B such that A sub I is equal to the class of A and A sub j is equal to the class of B. So according to lemma 2, either the intersection between these two classes is empty or they are the same class. But we know that they're not the same class because A sub I is not equal to A sub j, and so according to lemma 2, their intersection must be empty. So that tells us that A sub I intersect A sub j is empty. That means those two classes are disjoint. Okay, that's all for now.